Let me show you how we can assemble an adequate data path and how we can control the execution of instructions. Let us start first with instruction fetching, the instruction fetching data path. So how do we fetch an instruction? We have to provide the address of the instruction. The address is stored in the program counter, so I need a PC register. So the PC is very important. It's a very special register because it contains the address of the instruction, okay, that should be fetched from the instruction memory. So we have a PC register. Notice that the PC, the clock is connected to the PC because we only update the PC at the edge of the clock. And the address is connected to the instruction memory. So once we connect the address to the instruction memory, we get the instruction at the output of the instruction memory. So the address is the input, the output is the instruction itself. Notice that the output consists of 32 bits. So this is a bus consisting of 32 wires. At the same time, we should increment the PC by 4, because typically when you have sequential execution of instructions, you finish one instruction, you go to the next instruction. So I need an adder. So notice that this adder is going to increment the PC by 4. Okay, so we always increment it by 4 by a constant because we are going to point to the next instruction in memory. Remember that every instruction is 4 bytes in memory, so we need to increment the PC by 4. Okay. Now, the least significant 2 bits of the PC are always 0, 0. I'm showing them here in red, because all instructions are 4 bytes in memory. So therefore, the address inside the PC is always multiple of 4, because the instructions are also aligned. So therefore, their addresses are multiple of 4. And therefore, when you look at an address in binary and it is multiple of 4, the least significant 2 bits are 0, 0. So I can actually do an optimization here. I can actually forget about the least significant 2 bits, which are always 0, 0. Take the upper 30 bits of the PC and just increment it by 1. So I can actually now, rather than using an adder, I can just use an incrementer that will increment the upper bits of the PC. So this is my next PC. This is like a small modification, okay, to the data path. Okay, so this way, okay, by adding the upper 30 bits, it's like adding 4, but there is no need to actually to add 1, 0, 0 in binary. We can just actually add 1 to the upper 30 bits. I hope this is clear. Do you have any question about this? So that's just actually for instruction fetching, and we use an incrementer to update, okay, to compute the next PC. So the next PC will be now an input to the PC register, and therefore at the next edge of the clock cycle, we update the PC. So cycle by cycle, we can update the PC to point to the next instruction in memory. Of course, this does not take into account jumping and branching. This is just for the sequential execution of instructions. I still have to come back and deal with the jump and the branch instructions, but I'll talk about this later. Any questions about this? If you don't raise questions, then I'm going to assume that you understand everything. Okay, so please wake up. Okay, do not really go to sleep. Okay, just actually be attentive and raise questions. The same way that you do this in normal lecture when we have like face-to-face lecturing. It's very important. This material is very important because you need it for your project, and we are going to have it also as part of the material for the final exam. Right. I don't hear anyone. Everything is clear? Okay.
Yes.
Clear.
At that moment, it's
right.
clear.
So far, so good. This is very easy, very simple. Okay, let us see how we can now, after we have fetched the instruction. So now we have the instruction at the output of the instruction memory. By the way, did you see this material in the lab? Did you start the lab about the data path?
Not yet.
No.
No, not yet.
Okay, good. So I'm slightly ahead of the lab, so this is good. So now once we have the instruction at the output of the instruction memory, now what we need to do is that we need to execute the instruction. So first we have to examine the opcode of the instruction. We also have to examine the function code. So now we know exactly where they are, the opcode and the function code. because now the instruction is 32 bits. We have 32 wires. Okay, we have 32 wires. So we can locate that which wires are the opcode and which wires are the function code. I'm going to assume here, for simplicity, that the opcode equal to 0. So this will indicate that this is an R-type instruction. It's an R-type ALU instruction. So what we need to do is that we need to read two registers, RS and RT, and I need to execute the instruction by using the function. And then after that, we need to write the result back to RD. So RD here is my destination. So RS and RT are my source registers, and RT is my destination. So now what we are going to do, we are going to extend this data path. We need now a register file. So now we have designed the register file in a previous, I talked about this in a previous lecture. So this is actually my set of registers. This is actually my component. This is actually my component, which is the register file. It has now RA and RB. These are my source registers. So I can extract RS and RT. These are two fields that exist inside my instruction. I can use them as inputs, okay, to the register file, which is now a component. And the outputs, which are read, will be provided on bus A and bus B. So we can take bus A and bus B, and we can connect them to an ALU. This is another important component in my data path. So this is what I call data path. Okay. So these are the components and the wiring, the buses. This is my data path. Okay. So this is the path, okay, in which, okay, we're going to use to execute the instruction. So once we have the value of register RS and the value of register RT, these will be available at the output of the register file. And notice that these are 32 bits because every register is 32-bit wide. We're going to send them as inputs to the ALU, and we're going to execute the instruction. Now, in order to execute the instruction, we have to tell the ALU what type of operation to do. So therefore, I need to control the ALU. The ALU is going to compute an ALU result. The ALU result will be passed back to bus W. It becomes an input to the register file. Notice that RD is also an input because it indicates, okay, what is the destination register to write. Okay, so ALU results becomes data input. RD is my register. Okay, it specifies which register to write. And then at the same edge of the clock, we update the register file and we increment the PC. So the increment of the PC at the same edge of the clock. So this will happen at the same time. So notice that we are updating the PC and we are updating one register inside the register file at the same time, which is register RD. So this is very important to connect the clock to the PC and to the register file so that both will be updated at the same moment in time. At the same moment in time. Now we need to control this. We need to control the register file and we need to control the ALU. So for this reason, we need to control signals. So the control signals are very important. In the case of the ALU, I need the ALU operation. So how do we obtain this ALU operation? We obtain it directly from the function because the instruction has a function. The R-type instruction has a function. So this function is very important because it's going to specify the function of the ALU or the operation of the ALU. So this ALU operation is going to come from the function. So this is how we control the ALU. Okay, so we have to tell the ALU whether to add or to subtract or to do a logic operation like AND or XOR, or for example, to do a shift operation, shift left, shift right, and so on. So we have different functions and therefore we have different operations which are implemented inside the ALU. And based on the operation, the ALU is going to compute the ALU result. We also need another control signal, which is called register write. Now, this register write is to enable the writing of the register file. So notice that register write, okay, so this control signal is going to be a single wire. It is just a single wire. If this wire is 1, it means that it's going to enable the writing of register RD. And if the register write is 0, then it is going to disable. Now, why do we need this control signal? Because some instructions will not write anything to the register file. We'll encounter these instructions later. Some instructions in the instruction set don't write anything to the register file. For example, the branch. The branch does not update any register in the register file. It only updates the PC. So for this reason, we need to control the register file. So this is the importance of register write. So notice that register write is just a single wire. It can be either 0 or 1. 0 means that we disable. 1 means that we enable the writing of the register file. Whereas ALU up, notice that ALU up consists of multiple wires. We can have as many wires as needed, okay, to define all the ALU operations. And for example, if I have 16 ALU operations, I might need, for example, 4 wires, because I can specify, okay, 16 operations in binary. Okay, so that's really the idea of the ALU operation. Is this clear? Of course, this is not really the complete data path, because it does not take into account the immediate type instructions. It does not take into account load and store. It does not take into account branch and jump. So this is not really the complete picture. We are just trying to build the data path step by step, just to understand how we can build it. Yes, تفضل.
Instruction memory will determine what type of instruction we have?
No, okay. So no, the opcode, okay, will tell us what type of instruction we have. Okay, so what is missing in this slide is that we did not actually, we need the logic, the control logic. I'll come back to it later. So the control logic is going to examine the opcode, and then based on the value of the opcode, we're going to generate the control signals that are going to control the execution of the instruction on the data path. Okay, so this picture is not complete yet. This is not the complete picture. So it has some missing important part, which is the control. How do we control the execution of the instruction? So we control it by examining the opcode. So we need the opcode for controlling the execution of the instruction. So the opcode is going to tell us it's an R type, and based on the opcode and the function code, we can generate the control signals. So far we have seen only 2 control signals, ALU up. This is needed to control the execution of the instruction inside the ALU. And also we need register write, and this is another important control signal which is used to control the writing of the register file. This is only for an R-type ALU instruction. How about for an I-type, an immediate type? Remember, the immediate type, it has a different format. So now everything becomes exposed. One would like to implement these instructions inside the CPU. So there is no function code. Okay, there is no RD. Okay, there is only an opcode here, and there is a 16-bit immediate. That's it. Of course, we have RS and RT. Now, in the case of the I-type ALU instruction, RS is my source, but RT is my destination because there is no RD. We are going to write register RT. Okay, so you can see that now we have a deep understanding of these instructions. Okay, because now we understand their hardware meaning. We understand how these instructions are truly executed inside the CPU. So what we need to do is that we need now to define our data path for the I-type ALU instructions. So again, we are going to fetch the instruction from the instruction memory. This is always the first step. So the PC contains the address. That's the address of the instruction. The instruction memory contains all the program instructions. I'm going to assume that all the program can fit inside the instruction memory. But this is not the case, because usually the instruction memory is just a small cache. And therefore, I will need to talk about caches in great details later and how they work. Okay, they are a little bit complicated, so I'm leaving it till later. But for simplicity, assume that the instruction memory is just, it can fit all the instructions of a program. You provide the address, you get the instruction at the output. So this is the instruction. It's the output of the instruction memory. And this instruction consists of 32 bits. Now, the upper 6 bits, you can just look at the 6 wires. Just the upper 6 bits will be the opcode. So now the control logic is going to examine the opcode. And knowing the opcode is different from 0. It has a unique opcode for each I-type ALU instruction. It can tell, okay, what is the instruction that you are trying to execute. Like if this opcode was the opcode of an I-type ALU instruction, what we need to do is that we need to read register RS. Only RS, just we have only one source register, which is RS. We need to read this from the register file. So we connect it to the RA input because we're going to read this register RA. The output will be bus A. So now we connect bus A to the first ALU input. Notice that bus A is the value of register RS. So we have read one register. Notice that we don't really read, okay, RT. We don't really need RT for reading, okay, from the register file because RT is now my destination. So we connect RT to RW. Notice that I'm not using bus B. Okay, it's not connected to anything here. We're not really using because there is no second source register. There is only one source register. So now the second input to the ALU is nothing but the 16-bit immediate. Now I know that the 16-bit immediate are the lower 16 bits, so we can extract these 16 wires from the 32-bit instruction. So the 32-bit instruction will consist of 32 wires at the output of the instruction memory. So we can tell actually what are the 16 wires which are used for the 16-bit immediate, and we can extend them to 32 bits. So now we are extending the 16-bit immediate to 32 bits. So now we provide 32-bit input. Now the extension here can be either sign extension or 0 extension. This is very simple, depending, of course, on the opcode, of course. So now we have a 32-bit, okay, input, which is the immediate. The extended immediate now becomes 32 bits, and it's my second ALU input. So now we can say add immediate or end immediate or immediate. So we can have all of these instructions executed inside the ALU. The ALU is going to compute this ALU result. The ALU result becomes now my input to the register file. And then we can write this ALU result back to the register file, and the destination will be RT. So RT now is my destination register, okay? Again, we need to control, okay? So we're going to use, so we need the clock. The clock is essential because we have to indicate that when do we update the PC and when do we update register RT inside the register file. So two registers are updated, RT, register RT, and the program counter, okay? And they are both updated at the same edge of the clock, okay? Now, we need control signals. Okay, I need the control signal. Okay, ALU up. This is very important. This ALU operation. Now we are going to derive this ALU operation from the opcode because the opcode can tell us this is the opcode for add immediate, and immediate, or immediate, XOR immediate. Okay, so we have to add or we have to end or XOR. So therefore, we have to control this ALU. So this is the meaning of the ALU operation. So we derive it from the opcode field. Okay, this is not really shown in this slide. I'll come back to it later. How do we control the ALU? We need ALU control logic, specifically to derive the ALU operation. Now, we need register write as before, okay, because we need to control, to enable the writing of register RT. And we need another control signal here, which is called the extender up. Now, the extender up is just, okay, telling the extender to do 0 extension or sign extension. And because for some instructions, like add immediate, the immediate is signed, and therefore we have to use sign extension. Whereas in the case of AND, OR, and XOR immediate, these are logic operations. According to the MIPS architecture, we have to use 0 extension. So therefore, we have to tell the extender use 0 extension or use sign extension. That's it. That's here the extender operation. تفضل علي.
We use ALU operation. You said, for example, distinguish between add immediate and add without immediate.
Okay, so
will that
add,
matter? I mean, ALU will not.
Let me say something. Okay, let me say something that add and add immediate that will do exactly the same thing inside the ALU. So the ALU will do just addition. In the case of AND, the R type AND or the immediate type AND immediate, in both cases, the ALU will do the same operation, which is just ending. Okay. The difference is that whether we have the second input to the ALU as the value of register RT or is the immediate constant. So is it the immediate as the second ALU input or is it the value of a second source register? That's the only difference, okay, between the R type and the immediate type. I don't know if I have answered your question. Is it clear now or there is something else?
I didn't get it, Doctor. I mean, yes, I get the add and subtract, for example, will be the same operation for immediate or R type.
Yes.
But I mean, you said why we distinguish between ALU operation for the I type and
well,
R
for the
type.
I type, the ALU operation will come from the opcode because there is a unique opcode, okay, for every I type ALU instruction. Whereas in the case of the R type, the ALU operation is going to come from the function code. So the function code is going to tell us whether to add or subtract, and or XOR, etc. Okay? So the way that we control the ALU, okay, we need a special logic, which is not shown in this slide. I'm going to add it later, specifically to control the ALU. We'll see this. Okay, we'll see this in my next section. Inshallah, it will become clearer. Yes, Sam?
Victor, I have a question. Is it RT is never read. RT will always write over. We always write on RT.
صحيح. In the case of the immediate type, RT is my destination. In the case of the R type, RD is my destination. Then this is going to create a problem.
So,
why?
What about
because
the
I can
branch?
actually have two different. I need the same data path. I need the same CPU to execute both R type and I type. So let me show you the next slide. We need to combine the R type and I type data path. I cannot really use two different data paths. I cannot really design two different CPUs. Okay, one for the R type and one for the immediate type. So I'm going to combine them. So the way to combine them is to actually to add multiplexers. So I'm going to use here a multiplexer specifically for RW to indicate whether RW, whether to write RT or RD. So these are my inputs of the multiplexer. I'm showing here the multiplexer. Okay, a small thing here in yellow has two inputs, 0, 1, and there is actually one output. I need this multiplexer to select, okay, whether my RW, my destination is RT or RD. And I need a second multiplexer here at the second input of my ALU because I need to select, okay, whether bus B or the extended immediate should be my second ALU input. So this way we can execute both R-type and I-type instructions on the same data path. That's how we build data path. So now, because I have introduced multiplexers, I need to control these multiplexers. So I have to introduce, every time you introduce a multiplexer, you have to control it. So we need a control signal. So now we have to add more control signals. I need a control signal. So in addition to ALU up and register write, and also we have the extender up, I need two more control signals. I need register destination. This is a very important control signal. So register destination, if it is 0, we are going to actually to write to register RT. And if it is 1, we are going to write to register RD. So depending on the instruction, if the instruction was R type, then register destination should be 1 because we have to write to register RD. And if it was of the immediate type, we have to make register destination 0 because we have to write to register RT. So now it works. Now it works. You can see that now I can control, okay, what is my destination register? Is it RT or RD? And it all depends on the opcode, okay? What is not really shown in this slide is the control logic that's going to examine the opcode and generate these control signals. But at least I have identified that I need to control. I need to control what needs to be written inside this register file. I need to control my destination register, okay? The other thing that I need to control with this multiplexer is the second ALU source. So I need a control signal here, which is called ALU source. This ALU source can actually select my second ALU input. It can be the data on bus B. That will be the value of register RT. This is the case of an R-type instruction. Or it could be the extended immediate. Notice that this is the 16-bit immediate here, which is extended. Okay, so if ALU source is equal to 1, then my second ALU input will be the extended immediate constant. So this way we can control, okay, the execution of these instructions. So if it was an R-type, we select different control signals, so the control signal values will be different. Okay, so we select register destination to be RD, and ALU source will be 0, which is bus B. Whereas if it was an immediate type, we select register destination to be RT, because we're going to write to RT, and we select ALU source to be 1, which is the extended immediate constant. Okay? So that's it for today. Yes, Sam,
I have a question about the branch instruction.
We did not handle them yet. So far we cannot, this data path that we have seen here in this slide 29 cannot jump, it cannot branch, because there is no support for it. We are going to, this is not the complete data path. We are going to complete it, inshallah, in my next lecture. I will complete this data path by showing how to support the branch and the jump. Not only that, but also we need to support load and store instructions. These are not really supported in this data path. So this data path is incomplete, and therefore we have to make it more complete, inshallah, next time. And once we have the complete data path, then we need actually to define the control signals and implement the control logic. Okay, Amr?
Okay.
Okay. Any other question? Yes, Tfaddal.
Don't we need another multiplexer at the ALU OP to choose between the function and the operand?
No, that will be handled. No, we're not going to do that. We're going to actually to use a control, the ALU control itself, logic. So we're going to design a special ALU control logic that will handle this. So the multiplexer will be inside the control itself.
Okay.
All right, so we'll do this later. So this can be handled inside the ALU control. That will select whether the, so I did not show the control here, so we'll postpone this also to another lecture. Now, let us see how we can control these ALU instructions. So suppose that after fetching the instruction, notice that the instruction is available here at the output of the instruction memory. Of course, we need the control logic, which is not shown in this slide. I'll come back to it later. We need the control logic that's going to examine the opcode. So from the opcode, we can tell if it is an R type or it's an immediate type. So we have different opcodes. Now, if it turns out that this instruction is an R type ALU instruction, then my destination is RD. So we have to select here the register destination to be equal to 1. So this is how we control. We specify this control signal equal to 1, and therefore my destination register is RD. So we're going to select RD as the destination. Now there is no immediate here in the case of the R type. So therefore what we have to do is that we have to select ALU source to be equal to 0. So this will be the value on bus B. That will be the second ALU input. So notice that ALU source equal to 0. Okay, so this multiplexer, okay, will have its inputs as 32 bits. So this is a data value. And this is the value of register RT. So here RT is my second source register. Okay, so we have to select it. So ALU source will be equal to 0. Now ALU op is going to specify the function, okay, the ALU operation that comes from the function field. Register write will be equal to 1. This will enable the writing of register RD, which is my destination register. So this is how we control the execution of an R-type ALU instruction. In the case of an immediate type, okay, this is shown below. If you have an I-type ALU, again, we can detect this from the opcode. Okay, I'm not showing this detail. I'll come back to it later. Now, in the case of an immediate type, we have a 16-bit immediate. Now, RT here is my destination. So therefore, register destination, okay, this control signal must be equal to 0. So therefore, we select here RW becomes RT. That's my destination. This is the register that we are going to write to. Notice that my 16-bit immediate, okay, so my ALU source will be equal to 1. So we're going to select the extended immediate becomes my second ALU input. Okay, so it's the immediate itself is my second ALU input. And notice that ALU source is equal to 1. The ALU operation will depend on the opcode itself because there is no function code. And the register write will be equal to 1, indicating that we are going to enable the writing of the register file in the case of an ALU immediate instruction. For example, when I have add immediate or end immediate or immediate XOR immediate, okay, we are going to write to register RT and the register write must be equal to 1. Okay, is this clear? This is how we control the ALU instruction. So this is how we determine the values of these control signals. Right. So now concerning this extender, which is shown here at the bottom, this is going to extend here the 16-bit immediate into 32 bits. This is very simple and very easy. Now the 16-bit immediate will come from the instruction itself, but we have to extend it to 32 bits. And the reason why we have to extend it to 32 bits is that the ALU itself is going to receive a 32-bit value. Okay, so it's a 32-bit ALU, and both inputs must be 32 bits. So for this reason, the extender is going to extend it from 16 bits to 32 bits. There are two ways to extend. Either we can use zero extension, so all the upper 16 bits will be all zeros, or we can use sign extension. So here the sign bit of the immediate, okay, so this wire, okay, which is the most significant bit of the 16-bit immediate, becomes the sign of the immediate. This is when we have a signed immediate constant. So this has to be replicated 16 times. So according to the sign bit. So here we can use a control signal, which is for the extender. If this control signal, which is the extender up, okay, if this control signal equal to 0, then we end with 0. We get all zeros. If this extender up is equal to 1, it means sign extension, and therefore we get the sign bit replicated 16 times. It's very simple. Okay, this is how we need to implement the extender. So extender up equal to 0, it means that the upper 16 bits are all zeros, and extender up is equal to 1, it means that the upper 16 bits will be just the sign bit. The sign bit of the 16-bit immediate, which is this wire here, which is shown in yellow. Okay, so these are the details of the extender. This is how we extend the 16-bit immediate into 32 bits. Very simple, it's just one single AND gate that will produce the upper 16 bits. Okay, is this clear? Any question about this? Okay, I don't really hear. Yes, Omar, you have a question? Oh, okay, it's clear. Right. So we are not really done yet. We have to deal with load and store instructions. So we have to add now a data memory to the data path. Okay, so we add the data memory. So this data memory will have all the data. And for example, you can store an array, or you can store all the data for a given program inside the data memory. Now, the data memory should be addressed. We have to calculate the address. Now, we can use the ALU for address calculation. So whenever I have a load or a store, I'm going to use the ALU So there is no execution here, okay, on the ALU. There is no arithmetic instruction to execute. All what we have to do is that we have to access the data memory. But we can use the ALU for address calculation. So we are going to use the value on bus B. Sorry, we are going to use the value on bus A as my base address. This will be the first ALU input. And I'm going to use the 16-bit immediate. The 16-bit immediate here is going to be used here as my displacement, because remember the addressing mode, which is used by load and by store instructions, is that we use the 16-bit immediate as displacement. All the load and store instructions are of the immediate type. We have to remember these details because this is what we are going to implement. We are going to implement them on this data path. So now we use the ALU for address calculation. So the ALU is going to simply do an addition, add the base address to the displacement, to the immediate constant. And this is the address. So the address is sent to the data memory. Now, in the case of a load instruction, we take the data at the output of the data memory and we pass it back to the register file on bus W. So now we select 1 in the case when we are reading data, when we are loading data, okay, from the data memory. So the data will be available at the output data, at the data out, okay? This will be the output of the data memory. So we select it in the case of a load instruction. Notice that the ALU result will be selected if we don't have a load instruction. So if you don't have a load or a store, then in this case, we select the ALU result. Okay, so that will be the typical ALU instruction. But if you have a load instruction, we cannot select here input 0. We cannot select the ALU result. We have to select the data at the output of the data memory. So we need this third multiplexer. So every time I introduce a multiplexer, I need a control signal to control this multiplexer. Now, this is for loading. For storing, we take the value on bus B and we make it the input data, the data as input to the data memory. So we provide the address and data as an input to the data memory. That's in the case one would like to store it. Okay. So now, okay, we need a control signal here for memory read, for memory write, and to control this last multiplexer. So now we have added a third mux, and therefore we have to control it. So this control signal, which is write back data, if it is 0, we select the ALU result. If it is 1, this will be the case of a load instruction. We select the data out, the data at the output of the data memory, and we select it and we pass it back to the register file. Okay. So that's how we need. So now we have added 3 new control signals: memory read in the case of a load, memory write in the case of a store, and write back data to select, to control this multiplexer, to select either the ALU result or the data at the output of the data memory. So
can you repeat, Victor? Write back data from ALU result. What will be done?
So now if we have an ALU instruction like addition or subtraction, we don't really need to access the data memory. We just take the ALU result and we feed it back to the register file. But if we have a load instruction, then we cannot take the ALU result and feed it back. We have to take the data at the output of the data memory and we have to feed it back to the register file. Okay, so that's the importance of this multiplexer. So it's going to select, okay, whether the ALU result should be written back to the register file or the data which was read from the data memory. In the case of a load, it should be written back to the register file. Okay.
Okay.
Right. So let us take a look here on how we control the execution of the load instruction. So remember that load and store are both of the immediate type. So there is a 16-bit immediate, which is part of the instruction. There is no RD, there is RT. So we are writing to RT, not RD. So notice that register destination here, okay, must be 0 because we are going to write to register RT. Okay, so that's the importance here of this multiplexer. So we have to write to RT in the case of a load. we are going to enable the writing of the register file. So this is register write must be equal to 1, because we are going to write register RT. The extender up will be equal to 1. This is sign extension. So we have to extend the 16-bit immediate because it is of the immediate type. So this is the immediate displacement can be positive or negative. So this is why it's sign extension, not 0 extension. Multiplexer here, okay, the ALU source will be equal to 1 because we have to select the immediate. The extended immediate now becomes my second ALU input. Okay, so there is no data here on bus B. Okay, so therefore we have to select the immediate. Okay, so the value of our register RT is not important because RT is not a source, it is a destination in the case of a load instruction. The ALU, we have to control the ALU. So we have to say that the ALU operation is add. So in the case of a load instruction, we do addition inside the ALU. So what are we adding? We are adding the base address, which is available on bus A. So bus A here, okay, will be the base address. This is my first ALU input. And my second ALU input is the extended immediate. This is the displacement. Remember, it's displacement addressing. So we add the base address with the immediate. So this will calculate here my memory address. Okay, so this is the address for the ALU. Now, once we have this address, okay, we need to control this data memory. So I'm going to say that memory read is equal to 1 because it's a load instruction, and memory write equal to 0. Okay, so that's a load, it's not a store, so that's memory write equal to 0. The data will be available at the output of the data memory. Of course, after the delay inside the data memory, we get the output. Okay, we get the data at the output. Then we need to select this data out. So therefore, we need to select it using write back data. So write back data will be equal to 1. Okay, indicating that we are going to select this data. This will be available on bus W. And then at the end of the clock cycle, we use the clock to trigger, okay, when to write the data inside the register file. So the importance of this clock here is that it will indicate when the write will take place inside the register file. So we update the register file. We also increment the PC at the end of the clock cycle, at the edge of the clock. Okay. So that's the importance of the clock.
Dictor, the immediate 16, we use it like if we want to multiply, right? I mean, the first element will be 0 at register A0. If you want to the second element, I mean, in the word, I will see 4 register A0. That's
so
multiple of 4.
I mean, yeah, remember that in the case of load and store instructions, the immediate is used as a displacement. So for example, when I say load and I use, for example, let us say register, let us say T0 contains the base address, and I write actually 4 next to it. So this 4 here is the immediate. So it means that the address is T0 plus 4. Remember the use of the immediate in the case of load instruction and store instruction. That's the immediate. Okay, so we can use, for example, T0 as the base address, and the immediate is used as a displacement. This is the addressing mode, which is used by load and by store instructions.
Okay.
So is this clear now? The importance of the immediate, it is just a displacement in the case of for address calculation.
So this way we use the ALU in another way, just to calculate the displacement of the
so we are not using the
itself.
ALU to, so we are not using the ALU here to compute any result that we should be written to the register file, because this is not an ALU instruction. We are not really doing, for example, an arithmetic operation. Okay, we are using the ALU here differently to do address calculation. So the hardware is using the ALU for address calculation. So we not really need actually another adder for address calculation. I can use the adder which is inside the ALU. So this way I can actually reduce the cost of my hardware by using the same ALU for address calculation. The data will come from the data memory because we are going to read the data memory, and the data will be written into the register file, into register RT. So this is why register destination must be equal to 0 to select RT as my destination. Okay, is this clear? So that's for a load instruction. This is for load. In the case of store, we're going to write to the data memory. So let us take a look how we control the execution of a store instruction. So first we have to fetch the instruction from the instruction memory. So the instruction will be available here at the output. Of course, we have to examine the opcode because the opcode tells us if it is a load instruction or a store instruction or anything else. But I'm not showing here the control logic. As I said, I will come back to it later. So we need to examine the opcode. The opcode, if the opcode tells us that this is a store instruction, we can actually have different store instructions, like store word or store byte or store half word. Anyways, it is a store, okay? So what we have to do is that we have to read two registers from the register file, RS and RT. So here RT is a second source, it's not a destination. Because in the case of a store instruction, we don't write anything into the register file. So we read here RS and RT. So RS here will be available on bus A. That will be the value of register RS. And the value of register RT will be available on bus B. This is the data that we need to store inside the data memory. Okay, so now we say that what is the register destination? Well, we don't care about register destination because there is no register destination. So notice that I'm putting here X. X here is a don't care. I can choose X to be 0 or 1. The value of X will be some value. Of course, it's going to be either 0 or 1, but it does not really matter. Choose anything for X. It does not really matter. Why? Because nothing is written into the register file. So whether you make X 0 or you make actually X is equal to 1, either way is fine, okay? So this is why I put a don't care, okay, for register destination. How about register write? Register write, we do care about register write. It is 0. We have to disable the writing of the register file. So we cannot allow any value on bus W to be written inside the register file. So the store does not write anything inside the register file. So this is why register write must be 0. Okay, it must be 0 to disable the writing of the register file. Now, how about this ALU? The ALU is going to be used for address calculation exactly the same way that we have done in the case of the load instruction. So we are going to do an addition, but before that, the extender here, okay, we need to do sign extension as we have done in the case of a load instruction. We are going to do sign extension for the immediate in the case of a store, exactly the same way. We choose ALU source to be equal to 1. That will be my second ALU input. This will be the immediate. So we choose the immediate as my second ALU input, not the value on bus B, because we are going to use the ALU for address calculation. So we simply do an addition. So notice that the ALU up here is equal to add. So we always add in the case of a load or in the case of a store instruction, and we get the memory address at the output of the ALU. Now the data that we need to store will be available here at the input of the data memory. It's going to come from bus B. This is the value of RT. So therefore, we are going to connect this bus to the data input of the data memory. This is the value that should be stored in the data memory. And what we need to do now is that we need to control this data memory. So we say that memory read is equal to 0 because we are not going to read anything. But memory write should be equal to 1. So this is going to store the data which is at the input of the data memory at the specified address. inside the data memory. So we are writing the data memory. Notice that we are not going to read anything here, so there is no data at the output of the data memory. The ALU result, there is no ALU result that should be written back. So I really don't care about this last multiplexer. So I'm going to use for this last multiplexer, I don't care. So here write back data will be X. It means that we are not going to write anything into the register file. So whether you choose X to be 0 or you choose it 1, it does not really matter. Choose it any way that you want. And therefore, nothing is going to be written because the register write is equal to 0. Okay? So this is how we control the execution of the store. Now, still we need the clock. Now, at the edge of the clock, two things are going to happen. We are going to increment the PC. Notice that the PC will be incremented because we need to point to the next instruction in memory after we have completed the store. Also, notice that the clock is connected here to the clock input of the data memory. So we have to synchronize the write operation. So we have to synchronize this data memory. So while we are updating the PC, we are also storing the data inside the data memory. So these two things will happen at the same time, at the same moment in time. We update the PC and we write the data memory at the same edge of the clock. Notice that at the same edge of the clock, although the clock is connected to the register file, okay, nothing will be written, okay, into the register file. There will be some value here on bus W. Notice I'm showing it in gray. But whatever we have here on bus W, okay, will be ignored. Why? Because register write is equal to 0. So this is going to disable the writing of the register file, even though we might actually have here, for example, some data, some value. For example, the ALU result might be selected. It might be actually present here. So the ALU result is nothing but the memory address. But we're not going to write the memory address inside the register file. So this is why we are disabling the writing of the register file and nothing is written. Okay, is this clear? So this is how we control the execution of the store instruction. We are not really done yet. What is left? Okay, so I talked about load and store. I talked about ALU instructions, the R type, the immediate type. What is left?
Jump instruction.
What are these instructions? Sorry.
Jump.
Jump. Yes. We need actually to implement the jump and what else?
Branch.
Branch. Yes. We did not talk about these instructions. Okay. So let us talk about how we can add jump and the branch to the data path. Now, in order to implement the jump and the branch on the data path, we need to modify, okay, so I need to change the PC. Remember that in the case of branch and jump, we are not going to write the register file. We are not going to actually to update the data memory. All what we are going to update is just the PC. So all what we need to do is just to modify the PC. So now I need another multiplexer, which is at the input of the PC. So now the PC, we can just increment the PC. If we don't really have a jump, if we don't really have a branch, we simply can increment the PC and we point to the next instruction in memory. So we have this incrementer. So this incrementer is going to increment the upper bits of the PC. Notice that the least significant 2 bits are always 0, 0. So by adding 1, we are really adding 4, okay, to the PC to point to the next instruction in memory because the least significant 2 bits are always 0, 0. So in fact, we are adding 1, 0, 0 in binary, which is 4 in decimal. Right. So this is if we don't have a jump, if we don't really have a branch, that's what we do normally. But now, in the case of a jump, I need to calculate the jump target address. And I need to select here my jump target address. So this is input 1 to this multiplexer in the case of a jump instruction. So how do you know it's a jump instruction? We have to examine the opcode. The opcode is part of the instruction. So after fetching the instruction, we look at the opcode. If the opcode was a jump, we have to select the jump target address because the jump is always taken, right? Every time we encounter a jump, we have to jump. In the case of a branch, we have to calculate the branch target address. But the difference is that the branch is conditional. We may or may not branch. Okay, so this is called a conditional branch instruction. So now we have to say that, okay, what is the condition? Are we going to branch or we don't branch? If we are going to branch, we have to select input 2 here, which is the branch target address. So we need here to calculate the branch target address. I will explain to you this in a minute. This is if the branch is taken. But if the branch is not taken, we are going to select just the next PC address. We just actually go to the next instruction in memory if the branch is not taken. So in the case of a branch, we have to select between input 0, which is the next PC if the branch is not taken, or input 2 in this multiplexer. So we need to control this multiplexer. Right. So how do we determine the branch target address and the jump target address? Okay, for the jump, it's easy because we look at the 26-bit immediate. Now remember that the 26-bit immediate is part of the instruction itself. So the instruction is available here at the output of the instruction memory. So this consists of 32 bits. So we extract 26 bits. We know from the opcode that this is a jump because it has a unique opcode. So we extract the 26-bit immediate. So these are 26 wires on this bus. And we concatenate them with the upper 4 bits of the PC. And now we have the jump target. That's easy. That's what we have to do in the case of a jump instruction. So it's very easy to implement. Okay, because in the case of a jump, it is the addressing mode is very simple. It's just a direct addressing mode. So we just take the 26-bit immediate from the instruction, and we just concatenate the upper 4 bits. And this is my address. This is my jump target address. Remember that we are going to update the PC. PC contains an address, the address of the next instruction that should be fetched here, the instruction that should be fetched at the target of the jump. In the case of a branch, it is a different addressing mode. So in the case of a branch, it is a PC relative addressing mode. The reason why they choose PC relative addressing is that to make it position independent. I talked about it at the beginning of the semester when I talked about the branch instructions. So it does not really matter where you write the branch instruction in your code. The target is relative to where the branch instruction exists. So it's PC relative addressing. So what this means is that we have to take here the incremented PC. So that's my next PC address. Okay. We have to use an adder. Now this adder here is going to add the next PC address, which is here the incremented PC, with the 16-bit immediate. Now this 16-bit immediate must be extended. So in the case of branch, it is signed immediate. So it's sign extension. So this extender up must be equal to 1. So we use the sign extended immediate and we add it to the next PC address. In fact, we are adding it to the upper bits of the next PC, so the incremented PC. Remember, the least significant 2 bits are always 0, 0. So we use this adder here to calculate the branch target address. Okay. So this is how we calculate the branch target address. We need a separate adder inside the hardware specifically for calculating the branch target address. But this cannot really tell us if the branch is taken or not taken. We still have to execute the branch. So in the case of a branch, the branch itself is of the immediate type. Branch equal, branch not equal, and all the other branch instructions are of the immediate type. So what we have to do is that we have to read 2 registers, RS and RT. Notice that RS and RT are source registers in the case of a branch. So we have their values on bus A and bus B. So we have to pass them to the ALU. Now I can use the ALU to do a subtraction because in the case of equality, you can subtract and you can check if the result is 0 or not 0. That's very easy. So I can use the ALU operation here to do a subtraction. And once we subtract, we can actually use a flag, just a single flag, a 0 flag, that will indicate whether the result of subtraction is 0 or not. If it is 0, it means that they are equal. And if it is not 0, then they are not equal. As simple as that. Okay. So that's what needs to be done to determine the outcome of the branch, whether the branch is taken or not taken. Right. So we need to add a multiplexer here at the PC input. Okay, and what do I need also? I need a new adder here for computing the branch target address. This is to support the branch. We need a new adder. I don't really need a separate logic for detecting if they are equal or not. I can just use the same ALU for comparing the value of RS with the value of register RT. So we just use the same ALU. Now we need additional control signal because we have introduced this multiplexer. I need a new control signal. I'm calling it PC source. Now this PC source can be 0, 1, or 2. 0 means that, okay, we just go to the next instruction in memory. We just increment the address. That's it. 1 means that we have a jump instruction and we have to jump. So we have to select the jump target address. And 2, it means that we have to select the branch target address if we have a branch and the branch is taken. So the branch must be taken to select here input 2, because if the branch is not taken, we simply select input 0. So this multiplexer is just for selection, and therefore we have to control it. So we have only 3 possible values, 0, 1, or 2. Okay. Now we need also a 0 flag. This is important now. Why? Because we need to determine if the branch is taken or not taken. So this 0 flag is going to be produced by the ALU itself, because we are going to use the ALU to compare, okay, for doing comparison, okay, to check if the value of register RS is equal to the value of register RT. Remember that these values are available on bus A and bus B. So we use the ALU for comparison. All what we care about is equality, equal or not equal. So this is the importance of the 0 flag, okay? So if the 0 flag equal to 1, it means they are equal. If the 0 flag equal to 0, it means they are not equal. That's the meaning of the 0 flag. Let us take a look on how we control the execution of the jump. So first we have to fetch the instruction from the instruction memory. We have to examine the opcode. Now if the opcode is equal to jump, there is a specific opcode for a jump. It means that we have to jump. Okay, that's it. You don't really have to read any, there are no registers to read. There is nothing to execute. You just jump, that's it. So now we check here the opcode equal to jump. That's the first thing we have to detect from the opcode. And if this is the case, all what we have to do is that we have to control this multiplexer. Okay, just say PC source equal to 1. Select the jump target address, and this will be the new value of PC at the rising edge of the clock. Okay, we just change the PC according to the jump target address. That's it. This is all what we have to do. Now, what about the other control signals? What do we do about these control signals? Well, we have to define their values. Okay, we cannot ignore them. We have to have specific values for the other control signals. Okay, for register write, we have to make it 0. We cannot allow anything to be written inside the register file because the jump does not really modify anything inside the register file. How about the data memory? We have to make memory read equal to 0. We have to make memory write equal to 0. We cannot read, we cannot write anything from the data memory. In the case of the jump, jump is not a load, it's not a store. So there is nothing to read, there is nothing to write in the data memory. But how about the other control signals? Well, we don't really care about them. You can select anything, okay? We don't really care about register destination because nothing is going to be written inside the register file. So for register destination, it's going to be don't care. It does not really matter whether you select RT or RD. You can select anything. It can be 0 or 1. You can select here RT or RD. Register write will disable the writing of this register. ALU source, it does not really matter. ALU operation, it does not really matter. You can do anything that you want. Of course, we'll have here some value on bus A and bus B, but we're going to ignore them. We can do anything inside the ALU. The ALU result is going to be ignored. Okay. Notice that write back data, we don't really care about it. The extender op, we don't really care about it. Okay. So we don't really care about these control signals. Now, the clock edge means that we update the PC register only. So this is the only register to update in the case of a jump. Okay.
Doctor, I have a question. You said that in the jump we concatenate the 26-bit immediate with the upper
4 bits of the PC. Yes.
What do you exactly mean by concatenate?
You just put the bits together. That's
just put with. Okay.
Yes. Okay. So you take the upper 4 bits from the PC register itself. So in other words, don't modify the upper 4 bits in the PC. Just keep them the same way. Just update 26 bits in the PC and keep the upper 4 bits unmodified. This is another way to think about it. So the upper 4 bits in the PC, do not modify them. You can actually get this upper 4 bits from the PC itself. Or in other words, do not write them. Okay, just keep them. Okay, do not disable the writing of the upper 4 bits and only modify 26 bits. So the 26 bits, get it from the instruction itself and modify only 26 bits inside the PC. That's it. That's what I mean. So that's what will happen at the edge of the clock. We only update the PC because everything else is disabled. Now let us take a look at the branch. The branch is more interesting. So first we have to fetch the instruction. And then we have to examine the opcode. There are unique opcodes. So branch if equal, branch not equal, these have unique opcodes. So suppose that the opcode here says branch if equal. We have a different opcode for branch not equal. But let us focus on one of them. So suppose you fetch an instruction and this instruction turns out to be branch if equal. What you have to do is that you have to read two registers, RS and RT, from the register file. So their values will be available on bus A and bus B. So in the case of the branch, it's compare and branch in the same instruction. So we still have to compare. So we use the ALU. So first we have to control this multiplexer here. Okay. Notice that ALU source here is equal to 0. ALU source equal to 0 because we are going to select bus B. The second ALU input will be the value on bus B. This is the value of register RT. So we have to compare the value on bus A with the value on bus B. We have to compare the values of RS with RT. So in order to do this with this comparison, I can just use the ALU operation, which is called subtract. Just subtract them. Now the result might be 0 or not 0. So I need the 0 flag. So if the 0 flag is equal to 1, okay? If the 0 flag is equal to 1, this indicates that they are equal. Okay, so if the instruction is a branch if equal and the 0 flag equal to 1, so we have this if statement here. The opcode must be equal to branch if equal, and the 0 flag is equal to 1. Then select source to the branch target address. So therefore, my PC source must be equal to 2, which is the branch target address. Of course, the branch target address is computed by this adder, which is shown here. It's the output of this adder. Notice that the extender op is equal to 1 because we have to extend the 16th immediate before we do it. We do the addition to calculate the branch target address. Remember that the immediate can be negative or positive. It's signed. So negative means that we branch backwards. Positive means we branch forward. That's the meaning of the 16-bit immediate. So we have to calculate the branch target address and we have to select the branch target address. Now notice that here we say that this is the case if the 0 flag is equal to 1. Else, if the 0 flag equal to 0, if they were not equal, then we select PC source equal to 0. So here, I'm assuming that they are equal and the branch is taken. This is why I selected here the branch target address. But you can also have the other outcome of the branch. It means they are not equal and the 0 flag will be equal to 0. So we have to select PC source must be equal to 0. So therefore, we have two possible here outcomes of the branch, either taken or not taken. If it's taken, you select the branch target address. If it's not taken, you select the next PC address, which is input 0. That's it. So you have two possible here outcomes, and therefore you have two possible selections for PC source. 2, you selected when the branch is taken. 0, it means that you selected the next PC address is just selected when it is not taken. How about the remaining control signals? We have to be careful about these. We have to be very careful about the remaining control signals. The register write must be equal to 0. We have to disable the writing of the register file because the branch does not write anything to the register file. We have to disable here the reading and the writing of the data memory because it's not a load or restore instruction. So we care about these values. We must make them zeros. Whereas the remaining control signals, we don't really care about them. Since we are not writing anything into the register file, register destination can be don't care, anything. It does not really matter. The write back data can be a don't care. So we don't really care about this last multiplexer here. Okay, so because nothing is going to be written back into the register file. Now notice that at the clock edge, we use the clock again to update the PC. So only the PC register is updated at the edge of the clock, nothing else. So the register file is not updated. The data memory is not updated because this is not really a store instruction. Ali, tfaddal.
PC source multiplexer will be controlled by the flag and opcode.
Yes. So we need now to add extra logic that will generate these control signals. So what is missing now in this slide is what is the logic that is going to produce these control signals? That is what is really missing. This is not really a complete picture, by the way. So we are trying to discover the data path step by step by adding more and more instructions. We are trying to build this data path. So we have discovered, okay, that I need a multiplexer here, I need a multiplexer there, and I need actually every time I introduce a multiplexer, I need a control signal. Okay, what should be the value of this control signal? But I need the logic that will generate these control signals. This is what is really missing. Okay. Right. So the last topic here will be about the control logic. Okay. So once we have now seen the control logic, we'll have the full picture. Yes, Sam, you have a question?
The previous slide. Now the flags, the flag 0 here. For example, if we have another opcode, does it mean one branch and 0 don't branch always? Or
if we have a different instruction that has a different opcode, then we have to use, if it is a branch, let us say branch not equal, we have to use the 0 flag differently. If you have a different branch instruction, this is what you mean, right? Now, if you have something which is not a branch instruction, completely different from a branch, we're not going to use the 0 flag. And if you have, for example, an arithmetic instruction, an add or subtract, we're not going to branch. So the PC source will be equal to 0. So the PC source will be equal to 2 if we have a branch instruction and the condition for the branching is satisfied, is met. Yani we have to have a branch and the branch is taken. Then in this case, we select PC source equal to 2. If we have an instruction which is not a branch, so it does not even matter what the 0 flag is. We will have the flag in the hardware anyways, but we're not going to use it. Okay, is this clear?
Okay, thank you.
Right. Right. So what is missing? What is missing is the main and ALU and the PC control. So I need to talk about these things. We need to generate these control signals. So this is my data path. Okay, I'm just not showing all the details. Remember that when we fetch the instruction, we have the instruction here at the output of the instruction memory. So what I need is that I have to extract the opcode, okay, from the instruction. I pass it to the main control logic. The main control logic is going to generate the main control signals. I need to control the ALU. So I need here another control, which is called the ALU control. I can use the opcode and the function code because for R-type instructions, we have the function code that can be used to control the ALU. And the ALU control is going to generate the ALU up, the ALU operation. And finally, I need my PC control. So for the PC control, I need the opcode and I need the 0 flag to indicate whether the branch is taken or not taken. So this is now an input. So in addition to the opcode, I have the 0 flag. And the output will be the PC source that is going to control this multiplexer at the input of the PC. So that's it for today. I can see it is time. Let me stop recording.